This video follows on from the video called Properties of Alkenes, in which we looked at 4 reactions of alkenes and focused very clearly on the fact that at least 3 of those reactions were addition reactions. When lots of small monomers, alkene molecules, add together to make an enormous polymer molecule, they do so by addition. And in a minute we will have a look at the equations and the repeat units for some polymers and look at some of the properties. Before going on to talk about polymerisation, I wanted to go back to what we'd talked about in the previous video about the structure and the effect having a double bond in a molecule has on the structure of the molecule and its shape. This picture shows 2 molecules. The bottom one is totally saturated, 7 carbons, so C7H16, and you'd call it heptane, wouldn't you? I hope you can see that it is a fairly regular chain with similar angles around each of the carbon atom. If you look at the molecule on the green background, you will see it's only got 6 carbon atoms in it, but 2 of them are linked together by a double bond, so it's an unsaturated molecule. You can see around the double bond that it is a cis double bond, and you can see the effect that that has on the regularity of the structure. Now I want you to think about how easy it would be to pack molecules together. The molecule on the orange background, as I've said before, has regular angles, and I hope you will agree that it would be quite easy to pack lots of those quite close together. So the molecules can get close together, interact with one another, and have a substantial intermolecular forces, making it have a relatively high melting point. The molecule at the top, though, is going to be much more difficult to pack together in a neat way, and so it's going to have a lower melting point, even if it's got the same number of carbon atoms in it. So this goes to explaining the fact that animal fats that are saturated are solid at room temperature, and vegetable oils that have unsaturation, have some double bonds in them, perhaps more than one, are likely to be liquids at room temperature. Looking at ethene, the monomer, being polymerised into polythene, I'm going to draw the monomer, and I want you to copy me by drawing it in the shape of an H. When this molecule polymerises, it ends up producing a repeat unit like this. So all that we're doing is removing that double bond and turning it into a single bond. It's an addition reaction, so the double bond is lost, and we end up with a molecule that is made up of a whole series of repeats like that. So it's a large molecule, so we use that N to show we start off with a lot of N monomer molecules, and we end up with them all joined together into a long chain which has a repeat unit. So here is the monomer, here is the polymer, and the repeat unit is just this little bit here. So here's the repeat unit in blue. If we go back to black, you would call this the polymer, that is including the N, and this bit here is the monomer. The N is a large number. Polythene is used to make plastic bags, bottles, washing up bowls and buckets. Make a note of this in your handout, please. Here are 2 models of polymers. The top one is polythene and the bottom one, in the monomer, one of the hydrogens has been replaced by chlorine, so the monomer is chloroethene and the polymer is polychloroethene. Each of the chlorines has a mass of 35 or 37, doesn't it, compared to the hydrogens of a mass of 1. So the chlorines aren't really shown to scale here. You can imagine if those chlorines were a lot bigger than the hydrogens, they're going to have quite an effect on how wiggly that molecule is. So polychloroethene, it's also known as polyvinyl chloride or PVC, actually is quite a robust polymer that isn't very flexible. It is therefore used in window frames and guttering. It's also used to make cling film, but to make cling film they have to put masses and masses of a molecule in, which is called a plasticizer. And what that is like a very small molecule that works a bit like a ball bearing, lubricating, allowing the chains to move past one another. If the ethene is polymerized by heating under a high pressure, so you have a pressure of about 1,000 atmospheres, 1,000 times atmospheric pressure, a very high pressure and high temperature, you put in a trace of oxygen to start the reaction off, or alternatively peroxides. These are known as initiators. If you polymerize under those conditions, you do get something called low density polythene, LDPE. The reason that it's low density is as the polymer chains grow, you don't have much control over this, they have branches in them. So those branched chains mean that it's quite difficult for the molecules to neatly pack together, and it means that when you warm this set of molecules up, they're all different lengths of course, they soften over a range of temperatures, but it's not a very high temperature. More recently, a different set of conditions have been used to make polythene, and the type of polythene that is produced with these conditions is called high density polythene. The high density polythene is of higher density because it has crystalline structure. The molecules this time have very limited branching, which means that it's possible for them to get close together, line up, have stronger intermolecular forces between them, and so you get actually crystalline structure in the polymer. The conditions for making high density polythene are at low pressure and temperature, but this time you need special catalysts, and it's those special catalysts that have been discovered more recently that have allowed the production of high density polythene. If each of the hydrogens in ethene are changed to fluorines, you get the monomer tetrafluoroethene, and when that's polymerized you get polytetrafluoroethene. Polytetrafluoroethene, or PTFE, it's also trade name Teflon, is used to make non-stick coatings and some electrical insulation, as well as burette taps. Burette taps, it's really useful use of a non-stick polymer because the tap doesn't need greasing as it would if it was made of glass. Polypropene is made from propene, and can we stick to my rule, which was to draw the monomer in the shape of an H, and the H has got the double bond across the middle. So here's the double bond, there's the H shape, and of course you've got to have a CH3 on here. So there is the monomer turning into the polymer, just altering one of the groups from a hydrogen to a methyl group. Propene nitrile is the monomer that is used to polymerize into something called acrylan, which can be used to make fibres. Propene nitrile, we are writing it in the H shape. It's called propene because it's got 3 carbons, but the third carbon is actually hiding in the nitrile group. So 3 carbons, propene nitrile, there's the monomer. That of course polymerizes to make the H-shaped repeat unit, Ethanol is like ethanol, 2 carbons, but with a double bond. So C double bond C, it's got the OH group. So there's your monomer turning into the repeat unit and the polymer. Ethanol is, polyethanol is also called, it's called polyethanol, and it can be called polyvinyl alcohol, is actually soluble. So the polymer that you produce, because of that OH group in it, is able to dissolve. So it's quite useful because it's made into plastic bags that you can put laundry in, which means that once you put the laundry in there, say from a hospital, you just put the laundry into the washing machine inside the plastic bag, and the bag dissolves when the water goes into the washing machine. The polymers that we have been looking at are all called addition polymers. They've been made by addition reactions, and they're all resistant to chemical and biological attack. This is because they've got very strong carbon-carbon bonds or carbon-halogen bonds, and the molecules are really large, which makes it difficult for them to dissolve. Because they're not naturally occurring, it means there aren't any enzymes in any bacteria able to break them down, and no enzymes have evolved to do that. So that's a good point, because it makes the molecules or the polymers molecules that can be used for containers that aren't going to rot, aren't going to be degraded, resistant to chemical attack. However, there is a problem with disposing of the polymer because there is nothing that can break it down, so they're non-biodegradable. So therefore, disposal of polymers, we have to consider burning them, incineration, or recycling.